Welcome back to the deep dive. If your immediate future involves getting your head around ATPL theory, you definitely know that some instruments are just, well, they're fundamental. They connect the physics you learn with the actual safety-critical operations in flight. Today, we're diving into one that looks simple on the surface, but is technically pretty deep, the radio altimeter. Okay, let's unpack this. And we're doing it specifically thinking about how you master the ATPL material on the RA. This isn't just another gauge.
No, not at all.
It's the sensor that, enables those super precise, low visibility approaches, and it's a key player in stopping you from hitting the ground unexpectedly.
Exactly. Our mission here is to go way beyond just knowing it measures height. We need to dig into the physics behind it, the installation challenges, which are surprisingly complex, and crucially, the specific numbers and facts that you, the student, are likely to face in the exams.
Right, because when you look at the syllabus, the RA, the radio altimeter, it often gets lumped in with pressure altimeters.
Yeah, but functionally, and in terms of the accuracy needed, it's a completely different beast. We're talking height above ground level, AGL, right down to the foot.
Which is vital for certain phases.
Absolutely essential.
Yeah.
So we'll cover the mechanics, how it gets that incredible accuracy. We'll talk about the radio frequencies, key exam knowledge there, how the data looks on modern flight decks, both Boeing and Airbus styles, and, importantly, how installations compensate for differences between aircraft.
And let's stress this up front. The RA isn't just about the number on the display for the pilot. It feeds two other absolutely critical functions. We really need to hammer this home.
Agreed. This is high-yield stuff for your exams. Firstly, the RA provides that precise moment-to-moment height data needed for automatic landings. Whether it's following a classic ILS or newer systems, the flight control computers rely on it.
Okay, auto land. What's the second one?
Even more fundamentally, perhaps, it feeds height and, crucially, height rate information directly into the ground proximity warning system.
The GPWS, the system that shouts if things are going wrong near the terrain.
That's the one. Without accurate RA data, GPWS just can't do its job properly.
Okay, let's start right at the core principle then. We're used to instruments using air data, pressure, temperature, but the RA uses radio waves. And it achieves this mind-boggling accuracy, often quoted as plus or minus 1 foot at touchdown. How on earth does it manage that?
Right, it's impressive. The key is the technology it employs. It doesn't use the simple pulse radar idea, like, say, a weather radar might.
Okay, so no ping, wait for echo.
No,
Yeah.
It gets its precision by transmitting a frequency modulated continuous wave, FMCW. That continuous part is really important.
Continuous, so it's always transmitting.
Always transmitting, exactly. And crucially, the frequency of that transmission isn't fixed. It's constantly changing in a very predictable way.
Hold on. If the frequency is always changing, how does the receiver possibly know which frequency coming back corresponds to the signal it sent out just a moment before? How does it get a clean time measurement from that?
That's the clever bit of FMCW. So the wave goes down vertically, usually in an elliptical beam shape. It hits the ground, reflects back. The system measures the time for that round trip.
Okay, standard time of flight idea.
But here's the twist. Because the transmitted frequency is changing at a known constant rate, that's the frequency modulation part, the signal that comes back will have a slightly different frequency compared to the signal being transmitted right now.
Because the transmitter has moved on in its frequency change cycle during the signal's travel time.
Precisely. So the receiver just compares the two frequencies, the one it's currently transmitting and the one it just received back from the ground.
And that difference
in frequency, often called the beat frequency, is what gets measured. And because we know exactly how fast the frequency is changing the rate of modulation, that beat frequency becomes a direct, very precise measure of the time delay.
Which then translates directly into height. Clever.
It is rather neat. It turns a time measurement problem into a frequency measurement problem, which can be done very accurately.
Okay, so that makes the entire system utterly dependent on how predictable that frequency change, that modulation.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best